Good day, I'm Christy Marimayol and I will be discussing the parts of the cooling tower and the Merkel theory. In cooling tower, we cool water by exposing its surface to air and allow heat transfer to take place. 80% of the heat transfer is due to latent heat of vaporization of a small portion of water, while 20% is due to sensible heat or temperature difference of water and air. Towers are enclosed by casings and supported by frames. Water enters at the top part of the tower and is sprayed via nozzle so that it is uniformly distributed and effectively wets the field. This is an example of an induced draft counterflow cooling tower. In this type of cooling tower, water is exposed to a mass of air induced by a fan at the discharge coming from the bottom air inlet. The cooled water is received by the basin that is connected to the tower discharge. This is the cooling tower. From the video, you can see the main parts of cooling tower, which are the frame and casing, water and air inlet, nozzle, fill, cold water basin, and fan. Frame and casing give structure, support, and protection to other main components. Fill, usually made up of plastic or wood, is where hot or warm water is distributed and exposed to air. Cold water basin, on the other hand, which is located or near the bottom of the tower, receives the cooled water that flows down through the tower and fill. Other towers may consist of drift eliminators, louvers, and other components to ensure cooling efficiency. Drift eliminators capture water droplets and trapped in the airstream that otherwise would be lost to the atmosphere. Depending on the design, air inlet position may vary. It can either be located at the entire side of a tower if design is cross-flow design, or at the bottom of the tower if it is counterflow. Inlet louvers is generally found in cross-flow designs than in counterflow. Its purpose is to equalize airflow into the field and retain the water within the tower. Nozzle uniformly sprays and distributes water to achieve proper effective wetting of the field surface. It is usually made up of plastics and can either be fixed or sprayed in patterns. Depending on design, fans can be located at top or bottom, inlet or discharge. Generally, propeller fans are used in induced draft towers, and both propeller and centrifugal fans are found in forced draft towers. What is the difference of the cooling tower and refrigerator when both suggest cooling? Cooling tower involves the process of evaporation and not refrigeration, and its cooling is proportional to the temperature rise of the system, unlike with a refrigerator that can cool water without heat input. Lastly, cooling tower can only cool hot water to inlet air temperature, while refrigerator can cool below atmospheric temperature. Merkel theory states that the total heat transfer is directly proportional to the difference between the enthalpy of saturated air at the water temperature and the enthalpy of air at the point of contact with water, or the wet bulb temperature. In other words, under the assumption that each particle of water is surrounded by a film of air, the driving force of heat transfer is enthalpy potential difference. It is also mathematically expressed with these variables. These variables are also used in determining the KAV over L, or the tower demand or characteristics, expressed by the integral of the difference of hot and cold water temperature over the enthalpy difference of saturated air and air-water vapor mixture. Tower characteristics is the measure of order of difficulty for the liquid cooling requirements. Integration method of this and other parameters considered in the design will be discussed by Alan Jan Babasa.
Hi, I am Alan Jan Babasa and I will report about the Chebyshev method of integration and the different parameters that is needed to be considered in the cooling towers. Okay, for the Chebyshev method of integration, the formula for the cooling tower characteristic, which is equal to the integral of dt over hw minus ha from T2 to T1 will be equal to T1 minus T2 all over 4 times 1 over delta H1 plus 1 over delta H2 plus 1 over delta H3 plus 1 over delta H4, whereas delta H are the different values of HW minus HA at different conditions. Okay, so moving on, Here are the different parameters that is also needed to be considered in cooling tower operations: the cooling range, approach, makeup and recirculation, drift and drift loss, blowdown, static air horsepower or SAHP, and evaporation loss. So the cooling range is the difference in temperature between the hot water entering the tower and the cold water leaving the tower. The trend here is that increase in the water inlet flow rate will also increase the cold water temperature and thus decreasing the cooling range. On the other hand, approach is the difference of the temperature of the cold water leaving the tower and the wet bulb temperature. It is also the drive required for water evaporation. A requirement is that the cooling should be greater than or equal to the tertiary approach. Approach is directly proportional to the cooling range. A trend is that an increase of water flow rate will also increase the cooling approach value at constant wet bulb temperature. Okay, so now let us define makeup and recirculation. Makeup is the amount of water required to replace normal losses caused by bleed-off, dirt, and evaporation. On the other hand, recirculation is the process wherein part of discharged air enters back into suction of air. Another parameter is the drift and drift loss. Drift is the entrained water in the tower discharge vapors. Drift loss typically varies between 0.1 and 0.2% of the water supplied to the tower. The formula in finding drift loss is just the product of drift loss percent and inlet water flow. The unit for that is volumetric flow rate. The next one is blowdown. Blowdown discards a portion of concentrated circulating water due to evaporation. It lowers the system solids concentration, and it is calculated according to the number of cycles of concentration or ratio of dissolved solids in recirculating water over dissolved solids in makeup. The formula is W sub B is equal to WC over cycles minus 1. Static air horsepower or SAHP is determined by the given formula. Air volume times static head times density of water at ambient temperature all over 30,000 times 12. And finally, evaporation loss is the water quantity evaporated for cooling duty. Theoretically, the evaporation quantity works out to 1.8 cubic meters for every 1 million kilocalorie heat rejected. The formula for evaporation loss in meter cube per hour is equal to 0.00085 times 1.8 times the circulation rate in meter cube per hour times the difference of T1 and T2, whereas T1 minus T2 is the temperature difference between inlet and outlet water. Thank you for listening. The next reporter will discuss about the different equations that is used in cooling tower, and she is none other than Miss Michael Manilao.